Alright, welcome to your kinematics homework. Okay, so the first thing we're going to do is we're going to read through this and we're going to pull out each of the pieces of information we have and we're going to make a list. Okay, so what we have here is 2.2 meters per second squared. That's acceleration. So acceleration 2.2. I'm not going to write the units because I'm lazy right now. And then I see that we have 8.4 seconds, so that's time equals 8.4 seconds. And then let's see, right, of constant acceleration, the car reaches a speed of 44 meters per second. Now that's what it ends up going, so that's our V final. So we'll just write V equals 44. And what we want to know is how fast was the car going before it began to accelerate. So what we want to know is V naught. So we're going to look at this and say, well, which of these equations seems to do everything we need? Here's the one I think is the best, the big equation number one. And so we're going to substitute these values into here and then solve for V naught. So what we have is V initial is 44 meters per second equals V naught, which we're looking for, what is its initial velocity, plus the rate at which it accelerates, which is 2.2 meters per second squared, that's a 2 by the way, times its time, which is 8.4 seconds. So one of these seconds will cancel out one of those, leaving with meters per second. So that gives me, whoops, no, it happened again. That gives me 44 meters per second equals my initial velocity plus, what's that work out to be? That works out to be, that's a terrible plus, 18 point, let's call it 5 meters per second. And I got that by multiplying these together. And then since I'm adding this to this side, to find out what this is, I must subtract this from this side. So I get 44 minus 18.5 equals V naught. So V naught is going to equal 25.5 meters per second. That's how fast the car was going when it pulled onto the road. Now, I really should draw sketches, which would be the smart thing to do, but you know what? It's hard to do with this software, so I'm not going to. You thought it'd be easy. I thought it'd be easy to draw. It's really not. So let's just make a list of what we know. I see I have a balloon that's going in an upward direction at 12 meters per second, so that will be my V naught. It starts off going upwards at 12 meters per second, and that's positive because it's going upwards. Now, a person in the balloon drops a water balloon. The person in the balloon drops a water balloon. How far? So I'm looking for a change in distance. Does the water balloon have to fall in order to reach a downward velocity of 33? So I want to end up having a final velocity of negative 33 meters per second. And let's see, I have an acceleration that's equal to negative 10 meters per second squared, and what I'm trying to find is the change in position, which is really x minus x naught. That's what I'm trying to find. Well, that gives me an equation I see I need to use, which is going to be this equation. Well, let's just look at what I have. I have velocity, acceleration, and I'm looking for displacement. By golly, it looks to me like it's this equation right here. And we're just going to call that delta x, or we could say x minus starting position. So let's just go ahead and try this now. Alright, so we're going to use v squared equals v naught squared plus 2 times the acceleration times the change in position. Alright, so what we've got here is our initial velocity, well, our final velocity is negative 33, which we're going to square, equals 12, which we're going to square, plus 2 times negative 10 times delta x. So let's square these values and see what I get. Well, negative 33 squared is equal to, that's going to be 1089. So 1089 equals 144 plus, that's a plus sign, negative 20, I just multiply the 2 by the negative 10 right here, times delta x. So I gotta get delta x by itself. The first thing I'm going to have to do is I'm going to have to subtract this from both sides. So when I take 144 away from both sides, this is going to become 945 equals negative 20 delta x. So therefore, I have to then divide both sides by negative 20, negative 20, negative 20, and that means my delta x is going to equal negative 47.25 meters. In other words, it is going to displace 47.25 meters in a negative direction, which makes sense. Let's try our next one. A person standing on a cliff shoots an arrow upwards at 44. So since it's going upwards, I'm going to say my initial velocity is positive 44 meters per second. If the arrow lands at the bottom of a cliff 12.4 seconds later, so time equals 12.4 seconds, how high is the cliff? So we're looking for delta x. What is delta x? We know that acceleration is negative 10. So I know the initial velocity, the time. I'm looking for a delta x. So I think what I'm going to have to use is this equation here, big equation number 2, because I'm going to take delta x and I'm going to change it into x and x naught. Okay, so let's just go ahead and try this then. So since I'm changing it to x and x naught, what I'm going to say is x naught is going to be 0. That's where we're standing. And then in that case, what we're looking for is x. Alright. And let's just go ahead and give this a whirl. Alright. We have, we're going to use x equals x naught plus vt plus 1/2 at squared. So x is going to be what we're looking for. X naught is going to be 0. In which case, let's see, we have v. The initial velocity was a positive 44 meters per second times the time, which is 12.4 seconds, plus 1/2 of a. Now a is negative 10, so I'm just going to write negative 5, because that's half of negative 10, times 12.4 squared. Blah. Well, what that gives me is this. Alright, x equals, well, I can skip the 0, 44 times 12.4, that gives me 545.6. 545.6. And now I'm adding a negative value, so that's the same thing as subtracting. So, and if I take all of this here and enter it into my calculator, what I'm going to get is negative 768. So we have negative 768.8. And when I subtract those, what I'll get is an x value of negative 2232 meters. In other words, the bottom of the cliff is 223.2 meters. There's supposed to be a point there in a negative direction, which is what down is. Alright, we'll try our next one. Alright, the car in the diagram above is accelerating at, well, so I know what acceleration is. Acceleration in this case is going to be 4 meters per second squared. I don't know what the starting velocity is. So what I do know is that position A, which is here, here, so we'll say x naught. If this is the person, we're going to the left, so we're going to make x naught equal to negative 80 meters, and we'll let x, the final position, equal positive 220 meters. So this is a case where direction matters. And I know that the time it took was 6 seconds. Alright, so what I want to know is how fast the car is going when it reaches this final position. So what I want to know is the final velocity, is what I'm looking for. So let's see, let's take stock of what I have. I have x naught, a, t, and I'm looking for the final v. Looks to me like the one that's going to work is this one here. Alright, so keep in mind, these two look very similar to each other. The difference is this uses initial velocity and I add 1/2 at squared. This uses the final velocity and I subtract 1/2 at squared. So, let's just try this now. Alright, I'm going to say x equals x naught plus vt minus 1/2 at squared. Now I'm going to substitute into that. My x is 220 meters, that is. My x naught is minus 80 plus the final velocity I don't know, but I know that the time is 6 minus half of a, well a is 4, so half of 4 is 2 times, and the time is 6 squared. Well, the first thing I'm going to do now is I'm going to go ahead and I'm going to get rid of this 80. So since this is negative 80, I'm going to add 80 to both sides to make that go over, which is going to turn this into 300. 300, that's a terrible 300, equals v times 6 minus, well, 36, 6 squared, that's 36 times 2, that's 72, so minus 72. So I have to add 72, so what that's going to give me is 372. Equals v6. So I have to divide both sides by 6. So 372 divided by 6, it was going 62 meters per second. When it reached point B. So we don't know how fast it was going here, but by the time it got to here, it was going 62 meters per second. Let's try another one. Helicopter is ascending vertically at 5.5. So I have V initial equals 5.5 meters per second. It is when it's 105 meters above the ground, so x naught, so x at time 0 is 105 meters. A package is dropped out the door. How long does it take the package to reach the ground? So we're looking for a time. So time is what we'd like to find. And we do have to know, we'll assume we're on Earth, so we have an acceleration of negative 10 meters per second squared. And let's see, what equation do we need to use to do this? Oh golly, we're trying to solve for time. And we know the V initial. So since I know V initial and I know time, and I'm looking for time, I know acceleration, I think I have to use this one here. I think I have to use x equals x naught plus vt plus 1/2 t squared. That's v naught, by the way. Okay, so let's substitute in. Let's see, the final position is going to be 0, the ground. The initial position is 105 meters, plus the velocity we started off with was 5.5 times t, plus half of a is going to be -5 times t squared. And we want to know what t is. Oh boy, this looks like a quadratic equation. I'm just going to switch these around, put the square first and this last, and I've got a quadratic on my hand. So 0 equals -5t squared plus 5.5t plus 105. And so if I'm doing this as a quadratic, t is x, so t, and then this is a, this is b, and this is c. So I'm going to put these into, now, if you recall the quadratic equation, it is this: x equals -b plus or minus the square root of b squared minus 4ac over 2a. Alright, nothing for it but to substitute in. Okay, so x is going to be t, minus b is 5.5. Then we're going to say plus or minus the square root. Oh, I hope I can fit all this in. Can I move over some? There we go. Let's see, b squared. So that's going to be 5.5 squared minus 4 times -10. Well, I'm sorry, -5, because that's what a is. -5. And then that's times, and that's going to be times 105. Can I get over and put the 105? Okay, and then, and C is 105. All that under that. Golly, and that's, don't forget, this is all divided by 2a, so that's -10. So, if I put all this through, what I'm going to find is that t is going to equal -51.5 over -10, and that equals 5.15 seconds. That's a 5, by the way. If you can't tell doing a different color, that's supposed to be a 5. Okay? 5.15. 5.15. I'm sorry, it's so hard for me to write with this. So, sorry about the quadratic. That happens once in a while. Solving for time with these things is ugly, but hey, I did it, you can do it too. You're better at math than me anyway. Okay, I'm a little grumpy. My iPad just crashed and I just lost like a 30 minutes worth of work. So, bear with me. Try to keep a stiff upper lip. What? Alright, so here's what we got. A baseball passes upwards from a window that's 25 meters above the ground. Hang on a second, I gotta readjust my colors here. Alright, so in that case, I think what we'll do is we'll say that would be x naught, we'll say, is the ground, and we'll just pretend the ground is at 0 meters, and x is where it is now, which is 25 meters above the ground. Now it's going, at the end, it's going 12 meters per second, and I know that the acceleration is -10. I don't know what the time is, but what I want to find is what is its initial speed. That's what I'm looking for. So looks like I'm going to have to use this equation here. I'm going to use, whoops, I keep doing that. v squared equals v naught squared plus 2a times delta x. Now v squared is 12, and 12 squared is 144, equals v naught squared plus 2 times negative 10 is going to be negative 20, and the change is going to be positive 25 meters. So when I multiply negative 20 times 25, that's going to give me this. 144 equals v naught squared minus 500. So I have to add 500 to both sides, and when I do, this gives me 644 equals v naught squared. So I'm going to take the square root of both of these, both sides, and when I do, what that gives me is v naught equals 25.4 meters per second. That's how fast it left the ground. Okay. Now this next one, you know what? I don't know if it's very realistic. Hey, I'm not an archer, so give me a break. So here's what I'm going to do. I'm going to say, all right, the arrow is drawn back 75 centimeters, so I'm going to turn that into 0.75 meters. So I'm going to say, well, delta x equals 0.75 meters. And it leaves the arrow, so that's the final velocity, at 68 meters per second. And the starting velocity, I'm pretty sure, was 0 meters per second. It is most times we launch an arrow. And I want to know how fast it accelerates. Well, listen, I'm going to use that same equation again. So I'm going to say v squared equals v naught squared plus 2a delta x. V squared is 68. 68 squared equals 0 squared plus 2a times 0.75. Now, what I'm going to do is I'm going to go ahead and square 68. You know what I'm going to do? I'm going to say this. I'm just going to divide. I'm going to say 68 squared divided by, well, 2 times 0.75 is 1.5. So I'm going to divide both sides by 1.5. 1.5. Alright. And that's going to give me a equals that. And when I say, let's just try it now, if I say 68 squared divided by 1.5, that gives me a whopping 3,083. Woo! That's a rather crazy acceleration. 3,083 meters per second squared. To be honest, that seems a little large, but again, I'm no archer. Let's try the next one. A worker drops a hammer off a tall building. Ooh, not a cool thing to do. A person in an upper story office sees it go past the window at the initial velocity of 35 meters per second. Person in lower office sees it goes by at a final velocity of 78 meters per second. And I know the acceleration of gravity is negative 10. I don't know anything about the time, but what I want to know is the distance between them, so that's delta x is what I'm looking for. My goodness, I get the sense that Mr. Sampson likes this equation here. V squared equals v naught squared plus 2a delta x. In this case, we're solving for delta x, so we have v squared. V squared is 78 squared equals 35 squared plus 2 times gravity is going to be negative 20 delta x. Now I'm just going to leave it in this format here. I'm just going to say, well, what I got here is 78 squared minus 35 squared equals negative 20 delta x. So I'm going to divide both sides by negative 20, and it gives me delta x. I better put an x there. Delta x equals, in this case, let me do some quick calculation, 78 squared minus 35 squared divided by negative 20. As long as I watch my order of operations, what I'll get here in this case is negative 243 meters. That's a 4, by the way. Alright, let's keep going. Ooh, an astronaut problem. That means I get to mess around with gravity here. Alright, so what we got here. You know what? This is where it crashed last time. If you don't mind, I'm just going to save real quick. Okay, I'm back. An astronaut throws a rock downwards. Ooh, so what that means then is my initial velocity is in a downwards direction. Be careful with that. I screwed that one up the first time I did this. Let's see, off a cliff that's 127 meters high. So here's what I'm going to say. X naught is going to be 0, and the final one is going to be negative 127 meters because it's moving in a negative direction. I think that's going to help me here. It gets up on the cliff in 5 seconds, so time equals 5 seconds. And what we want to know is the acceleration of gravity on this planet. So since I know the initial velocity, I'll use this. I'll say x equals x naught plus vt plus v naught t plus 1/2 at squared. Now it's time to start substituting in. So our x, our final position is negative 127. Our initial position is 0. Our initial velocity is negative, so I'll put this in parentheses, 4.2 times our time, which is 5, plus 1/2 the acceleration of this planet times 5 squared. So I'm just going to go ahead and square 5 and make it 25. Alright, now what I'm going to do is I'm just going to go ahead and try to simplify. I say 127 equals, I'll forget the 0, negative 4.2 times 5, I think that's negative 21. Let me just see. Negative 4.2 times 5. Yes, negative 21. Negative 21 plus. Now I'm just going to take this here and I'm going to say, well, this is A times half of 25. Half of 25 is 12.5, so I'm going to say 12.5A. So what I have to do now is, since this is negative 21, I have to add 21 to both sides. So that's going to give me, let's see, what's that? It gives me negative 106. And then I'm going to have to divide both sides. Well, that's what I got when I got that by taking 21 away from this. And now what I'm going to do is I'm going to divide both sides by 12.5. And negative 106 divided by 12.5 gives me negative 8.5. So the acceleration of gravity on this weird planet is a little bit less than Earth. It's negative 8.48, which I'm just going to call negative 8.5 meters per second squared. Alright, enough of that sort of stuff. Let's go to these other ones. Okay, a bullet is dropped into a river from a very high bridge. At the same time, another bullet is fired from a gun straight down towards the water. If we neglect air resistance, the acceleration just before striking ground, keep in mind the entire time something is falling, it is going to accelerate at a constant velocity. It is going to be the same for both bullets. And the answer is it's going to accelerate negative 10 meters per second squared. Alright, that's an AP question, by the way. Someone standing on the edge of a cliff throws one ball straight up and another ball straight down at the same initial speed. If we neglect air resistance, I did this one for you in class, and what we find is that they hit at the same speed. And the reason is if I throw something up at 7 meters per second, it will go up, reach 0, and by the time it comes back to where my hand is, it's now going down at 7. So it really wouldn't matter if I threw it up at 7 and had it come back down at 7, or simply threw it down at 7. It's symmetrical in that regard. Weird, but it works out if you think about it. Now, a ball is thrown upwards, neglecting air resistance. What initial speed does the ball need to remain in the air for 10 seconds? Well, what happens is it's going to go up and stop and come back down. Now, these up and down problems, you need to keep in mind that this right here is where it reaches a velocity of 0. That's halfway through. So it's easy if you think about it in terms of it slowing down at 10 meters per second if it's in the air for 10 seconds, it reaches the apex at 5. So it goes from an initial velocity of whatever its initial velocity was, it's going to end up at 0 by the time it gets here. It's losing it at 10 meters per second squared. So that means it would have to be about 50 meters per second. The reason I say about is because really, let's face it, that's supposed to be 9.8, Mr. Fitz. But we're going to round it to 10 to make our life easy. All right, that's the homework. I'm sorry it's late. I'll get it published as soon as I can. Bye.